and L2b. That's
all right. So I'm doing this very second part for the reason that it is to let you know that you want to master, you want to really master the minimization. So this is a minimization question. Okay. Now, what is in the sentence that tells you that you are going to do a minimization, not maximization? What is in here that tells you that you are going to do a minimization and not a maximization? There's something in the question that gives you the clue. What is it? Yes, Francis.
okay. I think it says both field requires at least. I think the use of the phrase at least gives the idea of looking for the least combination of inputs.
Richmond.
Doc, he says the farmer wants to know how many bags of each brand to purchase to minimize total cost of the fertilizer, given the data above.
Correct. That is the answer. So the farmer want to know, you see, is there to minimize cost. It's clear there. The farmer wants to minimize cost of fertilizer. So that's what tells you that it's a cost minimization. But now you need to identify which ones are the decision variables. And when you look at the question and you look at the table and you look at all other factors put together, what are the decision variables? You can tell me. What are the decision variables? Because these are your first line of contact.
NPK and urea.
How do you know that those are the decision variables?
Because decision variables usually come with a price. And in the next years, over here, August will requires, say NPK costs 6 cedis, and the urea also costs 3 cedis. That means that is the decision.
Excellent, very good, well done, well done. Okay, so here you can see that NPK has been priced, and that is what tells you. So if you are writing the decision variable, okay, and you are actually giving a proper labeling or naming for it, you will say that let X1 be what? Let X1 be what? And the one who was reading it was using bags, so don't forget that it's in bags. So X1B, the yes, Steven.
X1B bags of NPK.
Or the number of bags, okay? Not just bags, but the number of bags of NPK. The number of bags of NPK what? Number of bags of NPK what?
In
NPK what?
Brand.
Yeah, NPK. What did they do to the NPK?
It's a fertilizer.
So then I'm saying that the number of bags of NPK what?
that will be required.
That will be required. That's the thing. Okay, that will be required. Or better still, that was used or to fertilize. Okay, used to fertilize. The number of bags of NPK fertilizers. You got to have something there. And remember, those fertilizers were either bought or they were used. Okay, they were either bought or they were used. And then, of course, you will have the X2 also nicely defined like that. The next thing is to go to the objective. Let's go back to the storyline. You got to master this, I'm telling you. The objective. Based on this, we know that objective is a minimization. So who can tell me what the objective function will be? what will be the objective function? Saying it. I want you to say it. Francis Andolfo. Yes,
Okay.
Miriam.
Yeah, it's going to be minimization of Z or the objective function equal to the price 6 cedis times X1 plus 3 cedis times X2.
All right, so it will be Z min equal to 6X1 plus the second one, which is, which is 3X2. This is it. Remember, it's a minimization. This was also in the question. And you can identify that within the question. Subject to some constraint. Just as in the maximization, we had labor constraint and then the milk constraint. Now here, what constraints do we have? What constraints do we have? Just as we had the labor and milk constraints in the maximization. In this minimization, what constraints do we have? Yes, Mira.
Yeah, we have the nitrogen constraint and the phosphate constraint.
Perfect. Okay, so now let's write that. If you look at the storyline, in order to produce NPK, you need 2 of the nitrogen. And in order to produce urea, you need 4 of the nitrogen. Okay, so remember, nitrogen constraint must go vertical here because that is what is being used to produce. So this NPK is your X1, urea is your X2. So if you are writing it, it will be 2X1 and then 4X2. Remember that this is not just available, but this is the minimum requirement. This is a minimum requirement of nitrogen needed to produce NPK and urea. Again, this is the minimum requirement. How do you know? It says that Ogbo's field requires at least is what symbol? Greater or equal to. So at least 16. So if you are writing the constraint now is going to be 2 of the X1, which is the NPK, plus 4 of the X2 is not less than or equal to, but greater than 16. This is a nitrogen constraint. And I remember, the more you have of the 16, the more, the better. Okay. So it means that you need a minimum of 16 nitrogen. So you can have as many as possible. Okay. Now, when you go to the storyline regarding the urea, it says that you need regarding the phosphate, you need 4 bags of phosphate to produce the NPK, 3 bags to produce the urea. Okay, and then you need no less than 24 pounds of the phosphate. So how will you write that? Who can tell me how to write that? Okay, how will you write that? Christabel.
4X1 plus 3X2 greater or equal to 24.
Very good. If you know what you're saying, that is very good. So that is phosphate. Okay. You got to understand what we are doing here because I'm going to ask you some deeper things. So if I asked you, and of course, the final thing is your non-negativity constraint. Okay. X1 and X2 should be non-negative. So I want to ask you to see whether you are following us. What is, how do I put it so that I can enjoy it? what is the total cost of NPK fertilizer? What is the total cost of NPK? You can tell me. What is the total cost of fertilizer for NPK? Francis.
I think that should be 6x1.
That is 6s1. That is correct. What is the total cost of fertilizer in this Ogbo market, or in this with this Ogbo firm? What is the total cost of fertilizer in this firm? Miriam.
So it will be 6x1 plus 3x2.
Very good. You're getting the picture. Now, don't get lost. Okay. Now, what is the minimum requirement of nitrogen needed to produce what is the minimum requirement of nitrogen used to produce Fanyogo and Fanchoco? What is the minimum requirement of nitrogen used to produce Fanyogo and Fanchoco? What is the minimum requirement of nitrogen used to produce Fanyogo and Fanchoco? Francis Aqua.
So I don't think the question talks about Fanyogo and Fanchoco.
Yeah.
Sorry, what is the minimum requirement of nitrogen used to buy NPK and urea? Sorry, NPK and urea. What is the minimum requirement of nitrogen that was used to buy this or to produce this? Yes, Francis. Yeah, Francis.
Okay, Doc. So that would be 2x1 plus 4x2.
2x1 plus 4x2. That's good. Okay. So you need to be able to understand what is happening here. So that word, that's the actual that was used. Okay. The actual of nitrogen that was used to produce the NPK and urea here is a 2x1 plus a 4x2. We don't know the exact amount yet until we know how many of the NPK and how many of the urea that we actually generated. Okay. So but once you know the x1 and the x2, then you can now know that, but you know that it's supposed to be more than 16. You know that it's supposed to be more than 16. So the first thing to do in this minimization is to plot the constraints. You remember I said we should plot the constraints. That's the first thing to do, you plot. So we are going to do the plot of the constraint. Of course, the first constraint is a non-negativity constraint. So your x1, which is a NPK, and then your x2, which is a urea. Okay, this is your non-negativity constraint that you plot. I'm sure this one is fine. Any question on this? All right. Now the next thing is to plot the constraint. Okay, that is the next thing to do. Plot the constraint. So you're going to plot the nitrogen constraint. What's the nitrogen constraint? Well, we know that the nitrogen constraint is 2x1 plus 4x2, and we know is greater than or equal to 16. I'm using the equal to indicate the minimum. So on the basis of this, if you are to do this plot, what would be the value of x1 when x2 is 0, you can quickly turn because you are plotting, you need 2 points. What's the value of x1 when x2 is 0? You know that that is 8. Okay. I know some of you know. Now, what is the value of x2 when x1 is 0? Stephen? 4. It's 4. Okay. So x1 is 8. Okay. And x2 is 4. So that's the first drawing. Okay. Remember, this is a minimization. So we are not looking at the area below the line. We are looking at the area above the lines, minimization. So the space we are interested in is the space above the line. Okay, let's go to the next constraint. The next constraint, if you check carefully, it was 4x1 plus 3x2 less or equal to, or greater or equal to, but then we're going to make it equal to 24. So what will be the value of x1 when x2 is 0? Anybody should mention the answer for me. Stephen?
6.
6, okay. So x1 will be 6 here. And then what will be the value of x2 when x1 is 0?
8.
8, very good. So now x1 is 6, that should be somewhere below this. Okay. X1 is 6, and then x2 is 8, that should be way above here. 8. Then you join the 2 lines, and that will be your next graph. So this first graph is a nitrogen, and then this is the phosphate graph. Okay. So you have your nitrogen, and then you have your phosphate graph. Now, how would you want to shade? The area we are looking for are all these. Okay, this is it. This is the area we are looking for. Everything here. Okay, so we want the minimum. Of course, there will always be a limit. So you normally bring a free disposability here to indicate that there's a limit to which you want to go. But this is the area. Okay, this is the area that we are actually dealing with. The feasible solution area is this whole point here, feasible solution area. Now, we need the feasible solution point. And the feasible solution point is going to be the corner point. Okay. Now, the previous one, the maximization, you created an ISO profit, if you can remember, where we're shifting it up or down, and the last place, it becomes tangent to the production possibilities. Now here we have an isoquant, more or less, a piecewise isoquant. And the last place that this isoquant to be is going to be the, you cannot easily say that it's going to be the intersection here. You can't. That would be a big mistake. You need to work out the things carefully and ensure that everything is in order before you know that you've done the right thing. So let's call this point, point A, this point, point B, and the last point, point C. We are going to find these corner points in this sense. But before we find the corner point, I want us to quickly convert this thing to the standard form. The standard form. Quickly. It is a minimization. It is a minimization. Nothing changes. The only thing that will change is that in a minimization, we don't talk about the slacks, we talk about the surpluses. We talk about surplus. Okay, so you are supposed to have a minimum of, so when a doctor tells you that you have diabetes and you are supposed to have a minimum of what do you call it? Well, let's put it this way. Yeah. Okay, no, forget about the doctor's one. So let's say that you are making a cake, some cake, and in the cake, if you want the cake to be a fantastic cake, you need a minimum number of sugar. Okay, like you need 6 sugars, which means you can have 8 sugars, have 9 sugars, but you need a minimum of 6 sugars to be able to get to the cake. So it is from that premise that we are doing. So in this case, when you are supposed to have 6, okay, and you get more, then it means that you have a surplus of that. You have a surplus of that. And so you got to, the key point is that make sure you deal with the minimum. Don't go above the minimum. But of course, because you are capable of going above the minimum. And again, let me use the diabetes thing. The doctor says that don't take any more than 2 cubes of sugar. Don't take any more than 2 cubes of sugar. He said, doctor, I will obey it. And then when you go home, you take 6 cubes of sugar. You have gone above the minimum requirement. You've gone above the minimum requirement. Okay, by how much? By 4. So that 4 becomes a surplus of that. And so in a minimization, the slacks, or in this case, the better word to use is the surplus are subtracted, but they are also called S. They are subtracted from the constraint, the left-hand side of the constraint. And then you convert the inequalities to equalities. So on the basis of this explanation, who can walk me through how to get this? Who can walk me through how to write the standard form? The objective function will not change. It will still be as adding zeros to the thing and then plussing them. But who can tell me how to write the constraint? Steven, okay, good, let's go.
Yes, so for Z minimum,
let me write it. Hold on. Z minimum,
Z minimum, we have 6x1 plus 3x2 plus 0s1 plus 0s2.
Okay, you ended at S2 because there are 2 constraints, isn't it?
Yes, please.
Good. Let's move on. Subject to.
Subject to, we have 4x1 plus 3x2 plus s1.
Well, in this case, it will not be plus s1.
Okay.
That's what I'm explaining. It will be minus s1. And of course, you're equal to what? 16?
16, yeah.
Now, why is it minus? Because this is surplus. Remember, you are supposed to use a minimum of 16 nitrogen, isn't it? So if I find my values for the urea and the NPK, X1 and X2, okay, and I substitute it here, it means that I'm expecting a minimum of 16, which is on the left-hand side here. I'm expecting a minimum value of 16. If there is something else, it means that I have gone beyond the minimum, and that will be captured here. Therefore, the slacks, if I move the slacks to the right-hand side and bring this one here, sorry, in this case, surplus, okay? The reason why it's a minus is that if I move it to the right-hand side, let's do that and see. If you move it to the right-hand side, you have 4x1 plus 3x2. Then you bring the 16 to the left-hand side, becomes minus 16. Then you take the s1 to the right-hand side, becomes plus s1. Okay, so if you go overboard, let's say that instead of using 16 minimum, remember it's minimum we are dealing with. Instead of using 16 minimum, you use 20. Then it means that you have 20 here minus what? 16. It means that there is a surplus of what? Of 4. So anytime you go above the minimum requirement, then you are incurring a surplus. Stephen, do you get it?
Yes, sir.
And then the second constraint will also be minus S2, isn't it?
Yes, please.
It doesn't change the non-negativity. The non-negativity will still be X1, X2, S1, and then S2 still greater or equal to. Okay. The non-negativity will always be as it is supposed to be. So note that the surplus become a minus And then when it comes to the maximization, it becomes a plus. All right. So now let's go back. We have drawn this. How do we find the optimal solution point? Well, it's very simple. Let's find the coordinates. So what are the coordinates of A? Quickly. Somebody should shout for me the answer. What are the coordinates of A? This you can see by looking at the graph. Coordinates of A. X1 is what? Wait. Yeah, Christopher.
0, 8.
0, 8. Very good. So you put that down. The coordinates of A are 0, 8. B. What are the coordinates of B? What are the coordinates of B? Of course, that one you need to find it simultaneously, isn't it? So let's go to C. What are the coordinates of C? Let's get the easier ones down first. Yeah, Miriam.
8, 0.
8, 0. Good. So now let's solve for the coordinates of B simultaneously. Now, what is the content? The content is this value, 2x1 plus 4x2, and then 4x1 plus 3x2. Okay. Now, one of the easier ways if you want to go through, you can multiply the top one. If you want to use the substitution approach, multiply the top one by 2. So when you multiply it by 2, you are now going to have 4x1 plus 8x2 equal to 32. Okay. So you can, on the basis of that, you can say that let the top one, this which is this one, minus this one. So the 4x1 minus 4x1 will be 0. 8 minus 3 will be 5. So you have 5x2 equal to 32 minus 24 is what?
8.
8. Is it 8?
32 minus 24. Yes.
Yeah, it's 8. Very good. So x2 is going to be 1.6. Okay. x2 will be equal to 1.6. Check a calculator. 8
Yes,
divided by 5.
Okay, it's 1.6.
Okay. So you get 1.6. Now you substitute that 1.6 into the equation. Okay, let's say any of the equation 3. Substitute it here. So you have 3 times 1.6. 3 times 1.6 is 4.8. 4.8. So eventually, if you do 4.8, you move it to the right-hand side, okay, you get 24 minus 4.8, 19.2. 19.2 divided by 4, and then you get
That will be 4.8.
4.8. Okay, so your final answer for this coordinate is going to be 1.6 and then 4.8. Fantastic. Now, which one will give you the minimum cost? Remember, which one will give you the minimum? Yes, Francis. Let's drop them one by one into the z function.
You mentioned the coordinates to be 4.8, 1.6, but I think 1.6, 4.8, but I think it should be the other way around since x1.
Oh, yeah, it's true. You're right. Fantastic. I was trying to see whether you were following. 4.8, 1.6, correct. So let's go to A and then drop it into the z function. Okay. Don't forget that the z function has always been 6x1 plus 3x2. 6x1 plus 3x2. So you have 6x1 plus 3x2. At point A, the x1 will be 0. So what is the value at point A for z? 3 times 8 is what? 24. Are you following me? Are you guys following?
Yes, Doc.
All right. Then at point C, let's deal with the C first. Okay. X2 is 0. So this will be 8 times 6. 6 times 8 for the value. 6 times 8 will give you what? It will give you 48. At point C, the minimum cost is 48. And then let's go to B. B, you're going to have X1 is 4.8, X2 is 1.6. So you have 4.8 times 6. Use your calculator. 4.8 times 6 is 28.8. Plus, use your calculator, 1.6 times 3. I just pray and hope that you all know what I'm doing. Okay. That will give you 33.6. 33.6. I'm using my calculator. So I'm expecting you to use your calculator. So on the basis of this, which of them gives you the minimum cost? Which one? Point what?
So point A.
Point A. So you can see that the minimum cost was not always the intersection point like it was before. The other one. It's not always going to be the intersection point. Okay. The minimum cost is exactly this value, which is the coordinates of point A. Let me take you back to the slides and you see something like this. So this is how you are able to find the final value, the final answer, okay, which in this case is your true minimum cost in this sense. So what it means is that in order to be able to minimize costs at $24, they will have to produce, how many? They have to produce, what was the value there? They don't even have to produce urea, NPK, right? They don't have to produce NPK, they just have to produce all by urea. Let me be sure that I'm giving you, okay. Yes. Okay, so
Yes,
you produce all with the urea, don't produce any NPK, and you minimize the cost at $24. That is how it works. And ladies and gentlemen, that brings us to the end of the entire caboodle. That brings us to the end of the